Hi everyone, my name is Timo Walter and I'm a committer in the Apache Flink software project. In these videos I want to share knowledge about Apache Flink, stream processing and general software engineering topics. This video will go deep. We will deep dive into the SQL engine. I want to talk about the SQL query translation from top to bottom. Maybe you have seen this API stack already in some of my other videos. It roughly outlines the different layers through which a SQL query will go. The highest layer is the table and SQL API. Once the pipeline is defined in those APIs, they will pass an optimizer and planner, and then the planner will prepare something that can be understood by a low-level stream operator API and executed in the data flow runtime. In this video, I will not go into the details of the data flow runtime nor the low-level stream operator API. I will focus purely on the optimizer and planner part. So let's get started. Of course, we start at the top. So that means we start with a SQL declaration. I have brought 3 examples, and for each of those examples, we will go from SQL through optimizer all the way down to the output of the optimizer. So the first variant is a basic variant. You will see that all 3 variants perform some kind of joining. And they have just slightly different modifications to trigger different pieces in the optimizer. So in this variant, I have created 3 tables, 2 input tables and 1 output table. So we have a transaction and a payment input table. Those 2 have timestamps, a TID for the transaction ID, amount, and type. And yeah, we want to join transaction and payment together based on a key. And in this case, we also want to join them together using an interval. So we assume that the payment comes in between when the transaction comes in or 10 minutes afterwards. The second watermark will slightly derive from default or standard SQL, as it is common in many databases, especially the DDL part, so the create table part, is different from vendor to vendor, and that also applies to Apache Flink. So for example, Flink's runtime supports the concept of event time processing or watermark handling. And yeah, like of course we had to model that also in the SQL language, which is why you can define a watermark in the create table statement. But nevertheless, we will not touch the query part of SQL. So the query part will always be a standard SQL, but yeah, Flink modifies some parts of the create table syntax. But of course, as you can see in variant 1, it's optional, right? Like you can also leave out the watermark. As you will see in the course of this video, watermarks in this case only serve as a optimization for saving resources. Apart from the watermark declaration in this example, everything else stays the same. So the SQL query has not changed. And variant 3 will actually not work with watermarks anymore, but it has defined a primary key on the TID column, both for the transaction table and for the matched table. And in this case, we are running this Flink SQL on Confluent Cloud. So we have also defined a changelog mode upsert. So the transaction table will use an upserting semantics, whereas the payment stays in append-only changelog mode. And what I want to highlight here on this slide is that literally every keyword can trigger kind of an avalanche. So every keyword has a special meaning, and it also means that it can have very large impact on the resulting plan that comes out of the optimizer and planner. So let's dive just through some examples and the keywords that we have seen in the three variants. First of all, there was a create table keyword. The create table keyword for Flink defines the connector, so from which external system we want to read. For example, we read from Kafka. But the connector and also the configuration of the connector using some properties will tell us about the changelog mode, or will tell the planner about the changelog mode. So is it append, is it retract, or is it upsert? Because this is very important to know for the engine. The engine needs to know what needs to be processed. So what kind of changes do I expect from the system, from the external system, and what needs to be produced to the target table in case the table is a sink, right? We also need to know what the target table can consume. The watermark for clause helps the engine and gives hints like, can intermediate results be discarded? When is it safe to trigger the result computation? So watermarks in general define a completeness marker. They are a completeness marker for the engine, telling the engine, I have seen everything up to time t. And if we know that, we can trigger the result computation, right? Like we can execute a window because we know, okay, everything until time t is there. Now it's time to release the window, compute an aggregation, and send it downstream. Or, for example, we can remove state because it's not necessary anymore for example, a join result. So yeah, watermark 4 is a completeness marker. Primary key, however, gives the engine information about uniqueness. So it is a uniqueness constraint. It tells the engine event with key K will occur one time or it will be updated. So if it's append only, it will occur only one time. If it is an updating table, then there needs to be a retraction and then an update, or it's upserting. And yeah, you can be sure that there is always just one key in the table. And if there is already a key, it needs to be replaced using update semantics. And yeah, for the engine, this is very helpful information because the engine can now reason about how do I guarantee the constraint for the target table, right? So like, is it possible, or do I have to throw an error if it's not possible? And also, like, can the join be executed on unique keys or not? Like, this information is very useful for having efficient plans. And then, of course, there are tons of keywords that the standard defines, and we are all familiar with those. Select, join, where. Those basically tell the engine what needs to be done, not the how. The how can still be defined by the engine, but at least the engine knows how much freedom do I have, how much can I optimize in order to produce what the user asked for. So this was about declaration, and we talked about keywords. Now let's dive into the next phase, which would be the planning phase. The planning phase consists of many different steps. Many of those steps are internal. They might change from Flink version to Flink version. Sometimes it's also necessary to introduce another intermediate phase. This is just like roughly showing you how the code base looks like. In the end, code is the only source of truth, And I will also give you some pointers to the individual classes, so you can also check out the classes yourself, and you can check if there has been a rule added or another phase has been added to do some pre-processing between the next phase or stuff like that. So everything starts with parsing and validation. Parsing and validation basically take the following input arguments. First of all, we pass the SQL string into the parser, but that's not everything. We already pass information about available catalogs, available objects in those catalogs, of course. So the parser and validator, they can look up objects, fields, columns, functions, and so on. Then the parser and validator will also get information about the loaded modules in this session, because Flink has a modular system, so not only core functions could be loaded, but also, I don't know, maybe some machine learning function module or additional functions. And then, of course, there is some session config. So all of these are basically the input for the parsing and validation step. And the output will be a calcite logical tree. So calcite, with this I mean Apache calcite. Apache calcite is also a project in the Apache Software Foundation that targets having it's kind of a library for common database tasks, such as like rules, optimizer frameworks, parsing, validation. So not every project needs to do this themselves. Like we can reuse common parts of an optimizer. So it's kind of an optimizer framework, and Flink also uses this optimizer framework. But as you will see in the following slides, we have actually in Flink, we have pretty extensively extended calcite at various locations. So we are still using calcite for the optimizer framework, for the interfaces, how to define a rule, but Flink has added a lot of custom rules to make Flink SQL possible. So again, back to the topic, we were talking about parsing and validation. So of course, the first thing that happens with a SQL text is that the parser will break it into a tree, an abstract syntax tree, with the help of catalogs and modules. The parser and validator will look up catalogs, databases, tables, views, functions, and all their types. Whenever necessary. And the validator actually is able to resolve all kinds of identifiers for columns, for fields, and also for functions. So this is a typical example that I show quite often. Like what does this query do? Like you have so many pies in this query, but the optimizer or like the validator is able to identify what is what. So there might be a pie catalog, a pie database, and a pie table in this database. And this pie might be a field of the table. And this pie here might be a nested field of this column. And of course, if you're just calling pi, it's most likely that you're referring to the mathematical pi function, right? That also doesn't need to use a parenthesis. So like the optimizer, the validator is able to resolve all these different identifiers to concrete columns, fields, and functions. And it also performs the necessary validation of all input and output columns and arguments and return types. So after this step, the calcite logical tree is in a correct state and is ready for being optimized. So like semantically, the logical tree has all types it needs, and is just valid content. So, as I said, I also want to talk about classes, so concrete classes, so that you can also look them up. You can check out Flink on GitHub, and yeah, you can check those classes. So the main drivers for parsing, the parser is partially generated out of some grammar, but still the main parsing logic you will find in the Flink SQL parser impl, and the validation you can find in the SQL validation impl. And in order to basically leave the SQL world and enter this relational algebra world where SQL doesn't play an important role anymore, but you really work on relational objects, this is done in the SQL to rel converter. So the output of this step is actually a so-called rel node. So we are entering the relational algebra world. Yeah, it's also written here, output is SQL node, then rel node. All right, so now we have the calcite logical tree as the input. And you will see now that there is not always a new tree. Sometimes it's also like different phases also operate on the same tree. So the next phase is the rule-based logical rewrite, which means this phase gets a logical tree but also returns a calcite logical tree. So what does Flink do in this phase? For example, it rewrites subqueries to join. So for example, exists or in can also be expressed using join and aggregations. This will be done in this stage. This simplifies the later processing. Also, we apply typical query decorrelation rules that you can also find in research papers, because Flink doesn't support any kind of loops during runtime. So yeah, like these correlated subqueries need to be decorrelated. We already start with simplifying expressions. For example, if you do a 1 plus 1 in SQL, there is no need to execute this 1 plus 1 during runtime. We can already evaluate that to 2. So general constant folding, like reducing the number of functions and rewriting, simplifying expressions. Yeah, for example, functions with literal arguments will be evaluated immediately. And there's also already some kind of filter pushdown where we initially push some filters into the sources. The main drivers here are the Flink stream program. So the Flink stream program defines all the phases that will now follow the rule-based and cost-based optimization rules. And since we are operating in streaming, or at least this is what I'm showing here, not batch mode, but stream mode, the main drivers are Flink stream rule sets. Like Flink stream rule sets contain all the optimizer rules that the Flink optimizer knows by today. And yeah, as I said, the input was rel node, and also the output will still be rel node, logical rel nodes. We did rule-based logical rewrites. Now it's time also to do cost-based logical optimization. So until also in this stage, everything we are doing is not rocket science. Like all databases do this. So like we are doing projection filter, we are doing projection push down or filter push down, also all the way to the sources. We are pushing aggregates through joins if possible. We are reducing the surface area for aggregate functions. So for example, an average can be rewritten into a sum divided by a count. We remove unnecessary sorting, aggregations, or union if they are just not required. As you can see, like all these are not very Flink specific optimizations. They are common database operations that you would expect in a logical optimization phase. Again, all these rules are defined by the Flink stream program and Flink stream rule sets. But now we are done with the logical rewrites and optimization. So the output is still a rel node, but a more specific rel node, because now we are entering the Flink logical rel node tree. So the next phases are more Flink specific and less generic relational algebra specific. So, and we continue. So now we are performing Flink rule-based logical rewrites. So Flink rule-based means now we are also adding concepts that only Flink understands. For example, this is where watermark pushdown comes into play, and also more projection pushdown in combination with the watermark pushdown, for example. Also, like specific operations like a rank operator that the Flink engine added. We will also transpose projection and filtering and push calculations past this rank operator and so on. Like very specific things. I will not go into the details here, but as you can see, the operations become more or the transformations become more Flink specific. For example, also the over window can be transformed into a top n node in certain cases. And this is a very important thing to mention here, and I will definitely also cover that in a dedicated video. This phase also makes sure that the timestamp column, the event time column, is in sync with the watermarks. So if you, for example, have defined a watermark for column X, the engine needs to make sure that this column X will not be modified by you. Because once you have defined a watermark over a column, this column becomes a time attribute column, and it needs to stay in sync with the underlying watermark system. So you're allowed to reference it, you're allowed to pass it on, but you're not allowed to modify this column. And yeah, like this is ensured in this phase here. So syncing the timestamp columns with watermarks. And as before, the main drivers stay the same, and also the output stays the same. It's just the first stage of the Flink logical rewrites and logical phase. And same as before, we had rule-based and then cost-based, and now comes I would say the Flink physical optimization and rewrites. So like the further we go into the phases, the more physical it will get. So again, the input here was a Flink logical node, rel node, and the output here will be a Flink physical tree. What does that mean? First of all, we are converting all logical nodes to physical nodes. So Flink physical rel is the name. And we will also add some very specific physical rel nodes. For example, here is the time where we add a changelog normalize. So this is where also this whole concept of changelog processing comes into play. Like changelog normalize and also tracking the changelog modes from source to sink through all the operators. So for example, if we add a changelog normalize right after the source, it might still be necessary to push a watermark past these special operators. So for example, a watermark through changelog normalize. And there is one important step, which is called the changelog mode inference. So this is where the planner basically checks is an update before necessary or not. So it starts basically at the sink level, and then from the sink level it will determine based on the operations whether retraction mode is required or whether whether the pipeline can stay in upsert or in append mode. Again, main drivers remain the same. These are the rule sets and the streaming program that are executing all these phases. And yeah, as I said, the output is a Flink physical rel node, and the Flink physical rel node knows exactly which changelog mode is produced and consumed by each operator. And that's basically it. It sounds actually very simple, but in reality, this is highly complicated. We have more than 100 rules in the Flink engine. But the important piece now is that once we have the physical tree, we can actually map the physical tree after optimization one-to-one to so-called stream execution nodes. Or in short, we usually call them stream exec nodes. And stream exec nodes are a very important intermediate representation. Basically, stream exec nodes are a recipe for the runtime. So they give an operator a name, so they give a SQL operator a name, and by this name we can actually resolve which operators or which pipeline parts we need during runtime in a Flink. And here is the list of all the supported stream exec nodes as of Flink 1.19. And yeah, basically you can, by just looking at the stream exec nodes, you know exactly what Flink supports, which operators does Flink support. So for example, calc. Calc is a combination of filtering and projection. So yeah, like filter and projection is combined into one operator called calc. So where clause and select clause are represented in the calc. We support sorting, ranking, over aggregates, union, join, limit, group aggregations, interval joins, temporal sorting, window table function. Right, so like all these stream exec nodes listed here, they already help you what is supported. So for example, if you want to know whether sorting is enabled, is supported, then take a look at the sort or the sort limit. And if you look into those classes, they are always prefixed with stream exec sort, for example. You can really see the recipe that is used for translating a sort into a Flink deck in the end. And the stream exec node have another purpose. The stream exec nodes are JSON serializable. So we can basically persist the output of the optimizer in JSON and write that to a file. And this file actually gives us stability guarantees. If you look into the API, we call this JSON graph compiled plan. So compiled plan is basically the stream exec node graph that is persisted in JSON. And you can read from this compiled plan, you can read this JSON in, and then the optimizer knows which execution graph to recreate and then to submit. And basically, this is where I want to stop today. Of course, there are way more layers in Flink, but I wanted to focus on the SQL engine and the query translation part. So yeah, the stream exec nodes, those classes are the end of the SQL stack. Those nodes have a translate method, and if you call this translate method, what will come out is the low-level stream operator API, namely stream transformations. And those stream transformations can then be passed to the next layer, which will then create a job graph out of it. So job graph is a representation that already contains concrete Java classes that need to be copied into the cluster and so on. And then the next layer will then create a job execution graph. The execution graph then has already the cluster information available. So it exactly knows what to execute where and how and so on. But yeah, like this is for the SQL engine, this is not super important. The SQL engine basically stops before the job graph, yeah, it will create a so-called stream graph, which then can be translated into a job graph by the next layers. But yeah, in any case, I think it is worth to check out the stream exec nodes. They exactly tell you how an operation is executed in Flink and how low level operator API is used. So, but now I also brought some examples here that really show you how the three variants that I introduced earlier are executed. If you remember, our first example had no watermarks and no updates. And this is basically how the logical tree looks like. So if you're doing an explain in open source Flink will show you the logical tree, the physical tree, and the optimized physical tree. So in logical tree, you will see there is a logical table scan, scanning the transaction and the payment, a logical join, logical filter, logical project, and logical sync. So this is the pure abstract syntax tree, validated, translated and validated from the given insert into statement. And after physical optimization, what you will see is, for example, the logical project and logical filter. Those have been combined and they have been pushed into the join operator. So the logical join has now a more complex join condition, where condition. And as I said before, the physical optimization also is aware of the changelog mode. So here there was no changelog mode involved, but now the sources and all the operators have a concrete changelog mode. All of that is in insert only mode, in append mode in this example. And here you would see a pipeline, how this whole thing would be executed. If you remember my talk about what is a stream processor or what is stream processing, we talked about the primitives for stream processing, and here you can really see how the primitives for stream processing are used in reality. So for example, there is a Kafka reader or two Kafka readers, because we are reading from two Kafka topics. And like the offset is stored in state. The join operator will have some state, keeping the left and the right side of the join in state. The calc for filtering and projection has no state. It's a stateless operation. And then there is the Kafka writer, which also needs to store in state what is the current transaction ID. And the checkpoints of Flink will actually will commit transactions. So here's also some example data. So there is some transaction and some payment coming in from the two Kafka readers. Of course, I'm always talking about just a single instance, but like this is a parallel setting. So all these operations are executed at a defined parallelism. In this case, it's a parallelism of 4. So the data comes in, then there is a shuffling step where we make sure that a common TID key ends up at the same join parallel instance. And yeah, the join operator will then join left and right side together. It will produce a concatenated output row. This will then be passed to the calc. The calc might do some projection or filtering. And then this is sent to the Kafka writer, and the Kafka writer will convert this internal row into a regular Kafka message, serialized into some Avro JSON protobuf format or something like that, and write it out to a Kafka topic. So here is example 2. If you remember, example 2 had exactly the same SQL query or SQL statement, but it had watermarks. So we defined a watermark for clause in the create table. And you can already see that in the logical tree, there is a logical watermark assigner added. So right after the table scan, both tables will now have a logical watermark assigner based on some column. This column is the time attribute column from now on. And then it's defined like given this column, how can we derive a watermark out of it? In that case, we are saying this column minus 2000 milliseconds will be the watermark. And the TS is now a timestamp column, so the engine will make sure to track modifications through the entire pipeline. So this is the logical tree, and now you can see that given that watermarks are present and our join actually performs an interval on this special marked time attribute here, the optimizer is able to detect that this is actually the representation of a Flink interval join. And here you can see the physical tree, and the physical tree will now reflect that using an interval join. So since our source supports watermark pushdown, you can see that the watermark generation has been pushed into the table scan, and is not part of the regular pipeline anymore. So the table source will make sure to apply watermarks and compute watermarks based on TS. And the interval join can leverage this TS now, and you see that the interval join has been detected, and also the window bounds have been extracted from this interval 10 minutes here, and still we are operating in changelog mode insert only. So that's basically the output of the physical tree. Now let's also take a look at the final runtime implementation. You can see the pipeline almost stays the same, but the interval join is now used instead of a regular join. So again, we are reading from two Kafka topics, and the interval join will still perform the join. The calc will also still create the projection, and we will create a Kafka message downstream. But the important thing now is that there are also watermarks traveling silently between the rows. And in this case, we know, for example, that the upper the transaction has a watermark at 12 o'clock, and the payment is still lagging a little bit behind. We are still at 11:55. But this information already helps us to determine the watermark of the interval join. So the watermarks are traveling from left to right, and you will see that we are calculating the minimum of all input watermarks, which means 11:55 is the current logical time of the interval join. So everything before 11:55 can actually be discarded because we don't need it anymore, and the 11:55, like knowing that it is 11:55, will trigger some timers for result computation. And once this result computation and state cleanup has been executed, the watermark will travel further through the pipeline all the way down until it reaches the sink. So, and this was variant 2. Now let's talk about variant 3, example 3. Again, we keep the SQL query constant. We remove the watermarks again, but this time we are also producing updates because the transaction table will create some updates for us. So as you can see, the logical tree is actually exactly the same as in the first example, but the physical tree looks different because the optimizer gets the information from the transaction table source scan that there are updates coming into the engine. So how do we see that? Here you can see that the table source scan actually produces an update after and a deletion. And since we are have only defined a primary key on one of the tables, not on both tables, there is only the left input spec that contains a unique key. So the join can basically detect whether both inputs define primary keys or not. And since there is also since there are updates, because in this case we are using Kafka as an input, and Kafka does not give us the full image of a changelog. The engine also added a so-called changelog normalize step. So changelog normalize will make sure that deletions contain the full row and not just a null value as it is common for upsert Kafka. So this is how the runtime would look in that case. So again, the payment stays append only, so there is no changelog normalize after this Kafka reader, but the transaction is updating, and we need a changelog normalize. So like the engine needs to normalize the changelog that comes in through Kafka, also maybe because the compaction has not kicked in. So like we cannot fully trust Kafka. The Flink engine needs to normalize the changelog, clean up the changelog before it enters the engine. So how does that look like? Kafka will send a update after for the transaction, and the changelog normalize will get this update after. It will compare with its own state. It will store the last seen record for this key in its state, and if it has not seen this key before, as you can see, it converted the update after into an insertion because it's the first time that the engine has seen this key. And then the insertion will travel through the pipeline together with the payment. And then everything else is as before. So you have transaction payment concatenated, joined, and then projected and sent out through a Kafka message. Let's now do a second key. Let's assume we see another update to the same key. In that case, the changelog normalize would not create an insertion anymore, but now it would really create an update after and an insertion. And yeah, and then the join would also create an update after, and this will then be projected. And as you can see in this case, the update after is traveling through the topology. So that should have given you some insights into how the SQL query translation works. I also hope that you will find it useful to just check out the code and look into stream exec notes or the Flink stream programs and the stream rule sets they can definitely help you getting started with the SQL engine. And yeah, it would be great to welcome you as a contributor in the open source project. Yeah, I hope you will also check out my other videos. Thank you for watching and see you next time.